All right, so hello, and welcome everybody on this beautiful platform PW. This is your physics mentor Gaurav Tiwari, and today, my dear kids, we'll be learning two interesting chapters, which is Newton's laws of motion and work, power, energy in this class, right? But before we start with anything, just first let me know if I'm clearly audible and visible. Hello. All right, so just let me know if I'm clearly audible and visible or not. Right, so hello, Shilat. All right. So this class is going to be about the basics of these concepts, right? So if you are in, if you are migrating towards grade 11th, grade 12th, from 11th to 12th, right? So there are a lot of concepts which are relevant, right, in the grade 12th. For example, there are certain problems in grade 12 that require you to know the basics of grade 11th as well. So you won't be able to solve really good problems if the basics is not very clear, right? So this is going to be our today's aim, right? Focus on the basics of these two chapters, right? Focus on the basics of these two chapters, right? All right. So without any further delay, let us start with today's lecture and let us talk about these things, right? So here it is. So let us talk about these things. So first of all, my dear kids, if you just move ahead and look into the NTA website, you will find that these are the topics mentioned in the chapter called as laws of motion, right? So in the laws of motion, you see that it starts with force and inertia. Then we'll talk about Newton's first law, second law. In between, we talk about momentum and all those things, right? So these are all the discussions that we need to do so that this particular chapter can be completed. So in our today's discussion, we will talk about this portion, right? We will not be looking more into the circular motion, right? But rest of the whole thing we will be discussing today, right? And this is the entire list of all the concepts that we are going to cover in the first part of the video, right? We are going to talk about first Newton's laws of motion, and once we have discussed that, we will be discussing about after that work, power, and energy, right? So let's start talking about it. So there will be questions, right? So my dear kids, if you can solve those questions, definitely I'll be giving you quizzes, right? Just look at those quizzes and try to solve it as well, right? Okay. All right, so let's start talking about it. So this is the first thing, the concept of inertia, right? So the chapter of Newton's laws of motion, it starts with this particular concept that is called as concept of inertia, right? This particular concept is something that is the beginning of this whole thing, right? So let us start with this thing, right? Here, imagine, right, I have this box over here, right? I have these couple of boxes over here, right? So see that this is the first box I have, this is the second box I have, right? And I am placing these boxes one over the other, right? So see that what is really happening. If I, these two boxes are fairly smooth. So right now, what I do, if I move the box that I'm holding right now really fast, see that. So you see, this box just drops from wherever it was. You see, instead of dragging it with the black box, you see what happens. You see, it falls downward, right? So the nature of this particular box, the tendency of this box shown over here is basically the inertial property. Let us understand why is that happening. So just focus on this part. Just focus on this part. So see, inertia is the tendency of a body to resist. What? To resist any change in what? Is a state of motion, right? Inertia is basically the inertia is basically the tendency of every single body if it has a mass. Inertia is tendency of every single body to resist any change in the state of motion or rest, basically. So anything that is at rest, right? Anything that is at rest. So this box was at rest above the second box, right? Now when I'm moving the second box, I'm not applying any force on the first one, right? So see that because of the inertial property, this one has some mass, it will resist any change in the state of motion. What is the state of motion right now? It is stationary, its velocity is 0. So when I move the box below like this, right, so it will resist any change and it will not change its position. These are the same effects that we see when we are in a car and all of a sudden brakes are applied in the car or a bus, right? So these are all the things that we have seen, right? I hope the ideas are very, very clear, right? Just the basic stuff. Okay. Now, what is force? Now, force is something you need to overcome the inertial effect, right? Force is something that you need to overcome the inertial effect. So, due to inertia, the state of motion of the body does not want to change. So if a body is stationary, it wants to remain stationary. And if the body is moving with a certain velocity, it wants to keep moving with that velocity, right? If you want to change, let's say that the body is moving at 10 meter per second, and now you want it to move at 20 meter per second. What is required? A force, a push is required, right? So my dear kids, what is a force? So force is something that you can apply to change the state of motion, right? The force can also change the shape, but we are not dealing with those bodies, right? So we are talking about only rigid bodies. What are we talking about? We are only talking about rigid bodies. Okay. So for example, here you see that I have this piece of paper, or I have this piece of paper over here, or you can take anything, right? For that matter, imagine that I have this polythene, right? And when I try to move this polythene, right, you look at that, okay? So when I try to apply force, initially it is stationary, and I applied force on it. So ideally, right, you see that when I apply force on it, so instead of moving, what will happen? It will collapse, right? So you see that collapsing this thing requires a force, right? So instead of moving, the force was wasted to change the shape. We are not dealing with these kind of bodies. We are dealing with solid bodies. So if you apply the force on a solid body, it should move, right? So this is what we are talking about, right? We are talking with rigid bodies, right? We are talking about the rigid body. In physics, what is a rigid body, by the way? A rigid body is something, if you apply a force on that body, the distance between the 2 points will not change, right? Here, when you are talking about this polythene, right, imagine that there were 2 points on this polythene, and when you apply the force on it, the distance between those 2 points will change. Right now the distance is this much, right? And when you apply the force on it, the distance is now lesser. So this body is not rigid body, right? We are not talking about this one, okay? So when we are going to discuss about the Newton's laws of motion, we will be talking about rigid body, right? So this is the body, right? You apply reasonable force on it. The distance between the 2 points will not change under the application of force. So we are discussing with these bodies, right? So yeah. So you see that what is the purpose of force? The force will change the state of motion of a body. The force will change the state of motion of a body. So if the body is stationary, with the application of force, it may move, right? And if the body is moving at a certain velocity, with the application of force, it can accelerate, all right? So we have seen it. There are 2 ways to apply the force: by making an actual contact with the body. Such forces are contact forces. For example, I'm pushing it, so I have to touch it. I cannot use the psychic power to move it, right? So those forces are contact forces. But at the same time, if I drop it, it will move because the gravity is pulling it. The earth is not touching the body, but still it can pull it. So the gravitational forces do not require the contact. They are non-contact forces. Similarly, the magnetic forces and electrostatic forces are also non-contact forces. You see that friction forces that are acting between the 2 bodies, surface and this body, are contact force. Normal reaction is again a contact force, and spring forces are also contact forces, right? While on the other hand, magnetic, gravitational, electrostatic forces, these are non-contact forces, right? Now let us talk about the Newton's first law, right? Till now everything is clear. Now let us discuss the Newton's first law. What is the Newton's first law? You see that this ball is rolling, right? Initially, this ball is rolling. Now think about it. If you want to stop it, right? If you want this ball to stop, what do you need? A force is needed, right? If you want to make this body to move faster or roll faster, what is needed? Again, force is needed, right? So we know that already. The state of motion, that means how fast the body is moving, and in which direction it is moving, right? When I use the word state of motion, that means I'm using 2 things in one sentence, right? What is the state of motion of this body? That means you have to tell two things: how fast the body is moving and in which direction it is moving. Changing the state of motion always requires a force. You see that? Imagine that you are riding a bicycle, okay, in this direction, and now you want to take a turn. Can you take a turn without changing the speed? You can take a turn, but the force is applied in that particular situation as well. Yes or no? The force is required in that situation as well. Yes or no? Right? So clearly we can say that a force is required not only to change how the speed of the body, but also the direction of the body. And both the sentences, both the terms joined together will become a state of motion, right? So the Newton's first law of motion is about that, right? So a body that is moving at a certain velocity will continue to move with that velocity in that direction only, unless a force is applied on it, right? Unless a force is applied on it. I hope the idea is very, very clear, right? So every body continues to be in its state of rest or uniform motion. That means the state of motion does not change unless a force is applied, external force is applied on the body, right? Now the thing is, next thing is momentum. In the 9th grade, you talked about the Newton's second law. You said it, F equals to m into a, right? But moving forward in the grade 11th, we don't say the Newton's law is that, right? There is slight variation in the Newton's law, the way we approach it, right? In the 11th grade and in the way forward, right? So how to explain the Newton's law right now? So we explain the Newton's second law or the value of force in terms of momentum, right? We explain the Newton's second law in the terms of momentum. So what is momentum? Okay. Momentum. You see that? Look at that. Here we have a block of mass 5 kg. And here we have a block of mass 50 kg. Right? Now some force is applied. Some force is applied on both of them. Right? Okay. Some force is being applied on both of them. Now, to know the effect of force, I saw that the first body started moving with a velocity. Let's say I'm observing this thing after 10 seconds, right? So the force was acting on the smaller body for 10 seconds and force is acting on a larger body for 10 seconds, right? After 10 seconds, I observed the smaller body is now moving at 20 meter per second. But the larger body after same amount of time is not moving as fast. It is only moving at 2 meter per second or 3 meter per second, right? So now think about it. Can I simply look at what is the new velocity and tell that where the force might be higher? Can I say that? Think about it. Can I say this body is attaining a higher velocity, which is why the force acting on this body will be higher? We can say no. Definitely, if you want to make a body move faster, you have to apply more force, right? If you want to move this block, let's say this box is there, and right now you want it to move at 5 meter per second, it requires certain force. If you want it to move at 50 meter per second, it requires even more force, right? So we can say that if we want to make a body move much faster, it requires much higher force. We know that, right? But by simply telling that, this velocity is not the only requirement that can tell us how much force is acting. Look at that. This body is also heavier, right? So clearly this one requires much larger value of forces. Yes or no? The body's second body is much heavier. So it requires the larger value of forces. Yes or no? I hope the idea is very, very clear. Just a second. Hello? Yeah. All right. So over here, we can discuss that, right? So you see that only the change in velocity is not the single parameter that can tell me how much force is acting on the body. So there is one more parameter, that is the mass of the body, right? So how much force is acting on the body and what is the change in the state of motion that it creates? Right now, the best parameter to address that, we need two parameters, mass as well as the change in velocity, right? And the product of mass and moment, velocity comes out multiple times when we are discussing the effect of forces, right? The effect, the mass and velocity both are required to be known, right? So we are calling the product of mass and velocity as momentum. Yes or no? Right. So this word momentum, which is the product of mass and velocity, clearly has a vector quantity. So its direction is same as the direction of velocity, right? So this word momentum helps us assess the value of force or the amount of force acting on the body, right? If you want to create a bigger change of momentum in the same time, right, you need higher force, right? If you want to change the momentum, you need force, right? If you want to change the momentum much quicker, right, then you need even higher force, right? Yes or no? So I hope the idea is making a lot of sense, right? Okay. All right, so let's continue to move forward. Okay. Okay, so momentum is this mass into velocity vector. This is the momentum, right? Let's continue to move forward. So this is the Newton's second law of motion. So you see that the force acting on the body is proportional to rate of change of momentum of the body. The force acting on the body is proportional to rate of change of momentum of the body. As I said, this is the second law, and as I said, the second law is explained in terms of change in momentum now, right? We are not directly jumping on and calling it m into a is the second law, right? We are calling it in terms of this, right? Force is proportional to rate of change of momentum. Okay. All right. So if you remove the proportionality sign and use the equals to sign over here, right, the proportionality constant is 1 over here. So force is equals to dp over dt. Okay. Now the momentum can be written as mass times velocity. All right. Now the mass being constant can come out of differentiation sign. So it will become m d by dt of velocity, right? If the mass is constant, there are a lot of situations when a body is moving and its mass does not stay constant, right? So in those situations, the mass will not come out of differentiation sign, but right now the mass is constant, it will come out of differentiation sign. And dv by dt is nothing but acceleration. So mass into acceleration will be the value of force acting on the body. I hope it is making some sense, right? Okay. The force acting on the body is mass into acceleration, but only when the mass of the body does not change as it moves. Think about it. A rocket. The rocket is simply moving because lot of fuel is burning inside it, and that is creating a lot of gases, which is creating a thrust and pushing the rocket upward. Rockets have so much fuel in it. That, you know, as it moves forward, it is burning at a very higher rate. It is burning, let's say, hundreds of kilograms of fuel every single second. And think about it, as the rocket is rising up, its weight is also reducing, its mass is reducing, right? So the rocket is moving. We cannot say that the rocket has same mass as it moves. Its mass is reducing as it moves, right? So clearly in that situation, we will not be applying m into a for the rocket. Yes or no? Because the mass is not constant. Here the mass was constant, came out of the differentiation sign. That is why we applied it. So this is the very important idea, right? Now let's move on and talk about the next one. So force is proportional to dp by dt. This is what we have said. Force is equals to k times dp by dt, and the constant over here is 1. Okay. So now the momentum is m into v, and that's how the same thing is there. So force is equals to m into a. We have said it, and this is the formula that we have seen in the 9th grade, right? And here I believe the idea is very clear that we are more or less interested in knowing that, right? We are more or less interested in knowing that what will be the format in these momentum terms, right? So let's understand and talk about the next idea. Okay, let's move on and talk about the next idea. Here we are talking about a word called equilibrium, right? Here we are talking about a word called equilibrium. So my dear kids, when the body is under translatory motion, so there are two types of possibility. Look at this situation, right? This kind of body can do two things. Let's say that here I am holding the body and the body is moving like this, right? So this motion, when the body is shifting from one place to another place, this is the translatory motion, right? When we talk about the equilibrium, this word in the translatory motion, the situation is different. But here the situation is like this. Let's say that I throw this body. So right now it will move, but it will also rotate like this. Yes or no? So in this situation, we are not calling it translatory motion. It is a general planar motion that involves translation as well as rotation. Yes or no? So we are not discussing the general plane motion right now. We are talking about the translatory motion, and we are talking about the equilibrium of translatory motion. Yes or no? So my dear kids, think about it. If we have a body And let's say that two people are pulling the body. One is pulling in this way, right? And applying a force of 100 Newton like this. And the other guy is pulling the body this way and applying the same force of 100 Newton like this, right? Will there be any change in the state of motion? Will there be any change in the state of motion? My dear kids, we can simply say that if two people are applying the force in the opposite direction, there will be no change whatsoever in the state of motion of the body, right? Because the net force is zero. Right? But as soon as the net force on this side increases, let us say that on the right side we have 110 Newton. So clearly the net force is towards right and the body will move with the net force, right? So I believe the idea is very, very clear that if the net force is acting on the body is zero, right? In that situation, the body will not accelerate. The body will not accelerate, or its acceleration will be zero as well. And in that situation, we will call it the body is under translatory equilibrium, right? The body is under translatory equilibrium. So we can say that in which situation the body will be under translatory equilibrium? We can say that when the net force acting on the body is zero, when the net force in all direction is zero. That means when the net force in x direction is zero, net force in y direction is zero, and net force in z direction is zero. When all of that is true, we will call it that the body is under equilibrium in all possible ways. I hope the idea is very, very clear, right? So now the next point is this. Force is mass times acceleration, but the better way of calling it is force is rate of change of momentum in a certain direction, right? Look into this formula, look into this question and try to solve it. Force is 6i minus 8j plus 10k and it accelerates with 1 meter per second square. What is the mass of the velocity? So try to solve it. Very simple problem, right? Very simple problem. You have a minute to solve it, right? So answer it in the chat box and we will put the, we'll see that how many of you are actually making correct answers, right? So what is really happening over here? A force vector is applied like this. So force vector is 6i cap minus 8j cap plus 10k cap, right? And it is accelerating with the acceleration of 1 meter per second square. So you now know that what will be the mass of the body. So mass is a number, right? How will you know that? So here we need to know the magnitude of force, because from the second law, force is mass times acceleration. So acceleration is force upon mass, right? Or we want to know the mass over here. So mass is force upon acceleration, right? Mass is force upon acceleration. So clearly, if I put the magnitude of force and magnitude of acceleration, I will get the mass, right? So acceleration, mass is force upon acceleration, as I said, acceleration, but we need to put the magnitude of force. So what is the magnitude of force? Under root 6 square plus 8 square plus 10 square. Under root 6 square plus 8 square plus 10 square divided by the acceleration. What is the acceleration right now? So the acceleration is 1 meter per second square. So divided by 1 and that will give you the answer. So it is 36, it is 64, add it up 100 and 100, 200, 200 by 10, which is 10 root 2. So 10 root 2, any option B is the correct option, right? 10 root 2 means option B is the correct option. I hope the idea is very, very clear. Let's move on and talk about the next part. Look at this question. A ship of mass that many kilograms initially at rest is pulled by the force of this much, right? So a ship of mass that many kilograms, mass is 3 into 10 to the power 7 kilograms, right? Initially is at rest, right? So initially this body, the ship was at rest. So initial velocity of the ship was 0, right? It is pulled by the force of that many newtons. So how much force is pulling the ship? It is being pulled by 5 into 10 to the power 4 newtons, right? Through a distance of 3 meters. So what is the distance? It is pulled by the distance of 3 meters, right? 3 meters. Assuming that the resistance due to the water is negligible, what will be the speed of the ship? So what will be the speed of the ship? That is what you have to figure out. What will be the speed of the ship? That is what you have to figure out. So you can definitely move ahead and talk about this particular numerical, right? You can definitely move ahead and try to solve it. Okay. So what will be the speed of the ship, right? So first of all, think about it. They are giving you the mass. They are giving you the force. and you can easily calculate the acceleration because the magnitudes are given. So acceleration will be force magnitude divided by mass. So clearly the force is 5 in 10 to the power 4. Mass is 3 in 10 to the power 7. Right? So just divide it and you will get the acceleration, right? Once you know the acceleration of a body, you want to know that it starts with zero velocity. It has a certain acceleration. A constant force means a constant acceleration, right? So think about it. If a body is moving with a constant acceleration, you have already studied in the kinematics equations of motion. If the body is moving with a constant acceleration, that is constant force is acting on the body, that means we can apply the simple equations of motion. V is u plus at, s is ut plus half at square. So we want to know the speed of the ship after certain time. So we can say that v is equals to v square is u square plus 2a into displacement. Right. So final velocity square is initial velocity square plus 2a. Acceleration you have calculated, you can put it over here, and displacement is 3 meters. That's it. So you can solve it and get the value of final velocity. I hope the idea is very, very clear, right? And let us move on and talk about the next idea. Okay. Yes. Chetank. Okay. So let's move on and talk about the next idea. So point 1 is the answer, right? And here you have solved it. A boy is pushing a box of mass 2 kilogram with a force of that many newtons. So force acting on the body is 20 I cap plus 10 J cap, right? So the boy is applying, the boy has a mass of 2 kilograms, right? The box has a mass of 2 kilogram, okay? It is pushing on a frictionless surface. If the box was initially at rest, so initial velocity of the whole thing was 0, then dash is the displacement along the x-axis after 10 seconds. So what will be the displacement along x-axis after how much time? 10 seconds. So clearly here we are adding up and we want to know that what will be the acceleration first so that we can apply it. Now think about it. It's a force 20I plus 10J, so it's a constant force. What will be the magnitude of this force? The magnitude of this force is under root this square plus this square. So under root 400 plus 100. So it is under root 500. Alright. Or 10 root 5. I hope the idea is very, very clear, right? So once you know the magnitude of force, which is under root this square plus that square. So 400 plus 10, 500 is 10 root 5. So once you know the magnitude of force and mass is there. So acceleration is magnitude of force divided by mass, which is 10 root 5 divided by 2. So it is 5 root 5. Once you know the acceleration acting on the body, my dear kids, right, you know the constant acceleration is there. Initial velocity is 0. Time is also there. So you can apply s equals to ut plus half at square. Because constant force will create constant acceleration. This part is 0 because initial velocity is 0. Half acceleration. Acceleration is 5 root 5. And time is t square is 100, right? So you just multiply it and you can calculate the final value, right? Okay. So I hope the idea is very, very clear. Okay. All right. So that's what they have done as well. So they calculate the acceleration. That is also no need to worry about that part as well. So they did just divided the force by mass, right? They divided the force by mass. So here the mass is 2 kilograms. So here I am also dividing the force by mass and getting the acceleration. So what they have done is they have first of all keep the force in the vector format and divide it by the mass. So the acceleration is coming out in the vector format. No need to worry about that. You can get the magnitude of acceleration after that, right? You can get the magnitude of acceleration after that as well. So that is also very cool. No worries about that part. So it is acceleration is coming out 10I plus 5J. So magnitude of acceleration will be under root 100 plus 25, which is under root 125, which is under root 5 cube or 5 square into 5. So 5 root 5. Acceleration is coming out 5 root 5 here and 5 root 5 there. So that is not going to change. You can either calculate the magnitude of force and divide that magnitude by mass, or you can divide the force by mass directly, get the acceleration vector and take the magnitude of acceleration vector. The idea is you need this thing. Okay. Look at this part. A body of mass 4 kg is experiencing two forces F1, F2. The acceleration acting on the body will be. So what will be the acceleration acting on the body? So clearly, what decides the acceleration of a body? Tell me, what decides the acceleration of a body? We can say that the net force acting on the body decides the acceleration of the body. So what will be the net force? The net force, two forces are F1 vector and F2 vector. The net force will be F1 vector plus F2 vector, right? So just add them up. 5i, 8j, 7k, 5i, 8j and 7k. Just add it up with 3i, 4j and 3k. 3i, 4j and 3k. Once you add it up, you will have the final value. It is 8i, 4j, 4k. Once you know the final, this is the net force acting on the body, the acceleration of the body will be decided by the net force. So the net force divided by the mass. So the net force divided by the mass will be the net acceleration. So acceleration, because the answer is in the vector format, you can directly divide the whole thing by the mass, which is 4 kilograms. So a mass is given as 4 kilograms right here. So divide the whole thing by 4. So it is 2i, 1j and 1k, right, which is option A. All right, let's move on and talk about the next one. At any instant, the velocity of a particle of mass 500 gram is this. So velocity of particle of mass 500 grams, which is 500 kilograms, right, 0.5 kilograms, right. So it is the velocity at an instant is given as 2t I cap plus 3t square j cap. No need to worry about that, right? Velocity is changing with time. So particle is accelerating. It is experiencing a force. The force acting on a particle at t is equals to 1 second is I plus x j cap. The force acting on the particle at t is equals to 1 is I plus x j cap, right? So what will be the value of x? Here we have to calculate that particular part. My dear kids, we can easily do that, right? How? We know the velocity like this, and we know that when we differentiate velocity, we get acceleration, right? When we differentiate velocity, we get what? Acceleration, right? So dv by dt will be acceleration acting on the body. Yes. All right. So dv by dt is nothing but the acceleration acting on the body, right? So differentiate that. So it will become 2i cap plus 6t j cap, right? Now, what will be, because this is force at t is equals to 1, so we need an acceleration which is also at the same time. So what will be the acceleration at t is equals to 1? So acceleration at t is equals to 1 will be 2i cap, and put t is equals to 1 over here. So it is 6j cap. Once you know the acceleration at t is equals to 1, you can multiply that with mass and get the force at t is equals to 1. So we can say that force at t is equals to 1 will be mass into acceleration at t is equals to 1. So mass of the body is 500 grams, which is 0.5 kilograms, and acceleration at t is equals to 1 is 2i plus 6j. 2i plus 6j. So once you solve it, the force will come out to be only I plus 3j, right? I plus 3j, and given the value, the force of the given value of force is I plus xj. The calculated value is I plus 3j. So in place of x, we have 3. So the option D is correct, right? Yes. Now the next part is impulse. Now the next thing is what we call as impulse, right? So what is an impulse? My dear kids, impulse is, you may have seen in a cricket, when the batsman is hitting the ball like this. So what really happens? The ball is making the contact with the bat for a very short interval of time. So far in our applications, when the body was moving and the force was acting on the body, so the force was consistently acting on the body throughout the motion, and it was accelerating the body, right? So that was another application of force. But there are multiple instances when the force cannot act on the body for that long, right? Force is acting for a very short duration on the body. In those cases, we are dealing with impulse of the force. In those cases, we are dealing with the impulse of the force. So what is the impulse, right? Impulse is when a force, when we talk about the timed effect of force, right? Like that. So force acting into the time duration for which that force is acting, multiply them, the value that you get is impulse, right? The force into the time duration for which it is acting is the impulse. My dear kids, what is this force? Focus on this value. Let's say that this is the bat. Okay, so I'm drawing a very large bat, right? So you see that when the ball is making contact with that bat, right, initially the force that you are applying is not maximum. You see, the ball is coming in contact and we are assuming that the ball is not deforming. So what is really happening? The ball is coming in contact with that particular bat, right? So right now the force is increasing and getting maximum, and then the ball direction will change. Then the direction of ball will change and it will go in some direction, right? So you see that the force value increases and then it reduces when the contact is removed, right? When the contact is removed, right? So you see that when the contact is being made, the force is increasing, and when the body is, you know, leaving that particular bat, right, the contact is removed, the force will drop to 0 again. So clearly the force acting during the impulse effect is not constant, right? So for example, here if I have this metal piece and if I hammer it, right, so you see that at the time t equals to 0, when hammer is just touched the metal object, right, hammer is just touching the metal object, what is really happening? At that moment the force was 0, but gradually in a fraction of second the force will be maximum, and then the hammer is removed like this, like a nail, right? I am hitting a nail, for example. So you see that the force is increasing, and when the contact is removed, again the force will become 0. So during that impulse effect, the force does not stay constant, right? The force increases and then drops to 0, right? So my dear kids, when we are talking about the impulse effect of the forces, right, when we are calculating the impulse, we cannot talk about one constant value of force, because as you see, when the contact is being made, the force is rising, and when the contact is losing, right, about to be lost, the force is reducing. So you see that we are going to talk about the average force, right? So whenever you are going to calculate the impulse, right, they will talk about the average force acting on the body for 0.2 seconds, right? Average force of 200 Newton is acting for 0.2 seconds. Clearly you can say that the 200 Newton is not acting for the entire duration, because you are not pushing it with 200 Newton like this, right? 200 Newton is not acting like this. It increases when the contact is being made. Now it is reaching to, let's say, 300 or so, but again it will reduce to 100 and 0 eventually when the contact is being removed, right? So in the impulse, we are not talking about one value of force, we will talk about the average value of force. I hope the idea is very, very clear. In the integral format, the impulse is like this, okay? So here you can say that if you have a force time curve, force, how the force is changing with time acting on the body, you can take the area under the curve and calculate the impulse. You can calculate the area under the curve and get the impulse, right? So impulse is nothing but a vector quantity. Its dimension is mlt minus 1, SI unit is kilogram meter per second, and all of that, right? So look into this thing. Now this is again a very, very important relation. It is called as impulse momentum relation. This is a very, very important relation, right? We can call it impulse momentum equation. What is that? You know, the force acting on the body is rate of change of momentum dp by dt. So dt will go on the other side. It will become f dt equals to dp, right? F dt equals to dp, okay? So this whole thing, on the left side, we are talking about the impulse, okay? On the right side, we are talking about the momentum, all right? So this equation is relating the impulse with the momentum, so called, we are calling it impulse momentum equation. So we can say that the impulse imparted to the body is equals to the change of momentum that is caused to the body, right? So we can say that impulse imparted to the body is equals to the change of momentum that we are causing in the body, right? I hope that is very, very clear, right? So you see that impulse is integral f dt. So I have already said it. So the area under the curve, this is basically the area under the curve, ft curve, between ti to tf, right, between the initial time and final time. So if you have a graph between force and time, how the force is changing with time acting on the body, right, how the force acting on the body is changing with time. So you take the area under the curve between two time limits. This is basically telling you the impulse imparted during that particular duration, right? Look into this situation. Figure shows the estimated force time graph for a baseball struck by the bat. So clearly, you see the force is rising and then it drops suddenly, right? From this curve, determine the average force exerted on the ball. So what will be the average force exerted on the ball? We cannot calculate the average of all the forces. You see that the force is increasing, the contact is being made, all maximum force is there, and then it reduces when the contact is about to be lost. My dear kids, in this duration, if you take the area under the curve, so what will happen? You will calculate the impulse. So impulse is that area, 1 upon 2 base into height, right? Area, that is the impulse, okay, I. And you know that impulse is average force into time, average force into time. So average force is going to be impulse upon time, impulse upon time. That is the average force acting on the body. This is the key concept behind it. This is the main concept behind it. So what is the main concept? The area under the curve is representing the impulse. And if you divide that area under the curve with time, you can calculate what will be the average force during the entire journey, right? So now only the calculation is there. So area, how will you calculate the area? Area is 1 upon 2 base into height, like this. So you can calculate like this. What is it? 2.5 minus 1, because this is 2.5, this is 1. So this part is not there in a triangle, only this is there in a triangle. So this is why we are talking 2.5 minus 1, right? So the base of the triangle is this, and this is how we can calculate the area. So area by time, impulse by time, right? Impulse is area by time, impulse by time is nothing but the average force acting on the body. Now, let's talk about the Newton's third law, which is the last law of NLM, right? Newton's third law, or the last law of NLM, right? What is that, and what do we get from this particular part, right? My dear kids, Newton's third law of motion, talks about this thing, right? Here, for every action that is acting on the body, there is equal and opposite reaction. For every action, there is equal and opposite reaction. We know that. It's a famous movie dialogue now, right? But the main idea is action and reaction forces don't act on the same body. Action force acts on one body while the reaction force acts on the other body, right? So we can say that action and reaction forces are there, right? Action force acts on one body, right, while the reaction force acts on another body. All right, they don't act on the same body. There is equal and opposite reaction. So action forces, for example, here you are burning up the gunpowder, and that gunpowder is going to create a lot of gases, which is going to push that metal object or the cannonball in the forward direction. So basically, this cannonball is being moved, is experiencing a force in this direction, and as a recoil, the cannonball will push this cannon itself in the backward direction, right? Which is why we have this stopper, right? Okay. So yeah, so here you can see that when this guy is going to jump off the boat, the guy will move in the forward direction, but the boat itself will move in the backward direction. Here you can see in the rocket and classic example. So this is the water rocket. So what is really happening? The water is coming down and pushing the, giving the thrust in the downward direction. And as a resultant, the rocket itself is being pushed forward, right? Okay. All right. So let's talk about the next idea. This is the law of conservation of linear momentum. So law of conservation of linear momentum is very, very important. What is this? Let us talk about that. Okay. Law of conservation of linear momentum. So here we know that force acting on the body is rate of change of momentum, dp by dt. Okay. If the force is constant, then what will happen? That means the acceleration will also be a constant thing. But now look at that. We are differentiating this quantity to get the value of force, right? If this quantity is changing, if the momentum is changing, that means there is a force, right? But if the momentum itself is not changing, if the momentum stays constant, if the body has a mass m and it is moving with a velocity v, right, and it is not changing, So momentum stays constant. What does that mean? D by dt of a constant is 0. D by dt differentiation of a constant is 0. So that means the force acting on the body is 0, right? So read it in this way. We can say if the momentum acting on the body is constant, that means there is no force acting on the body. Read it from here. If there is no force acting on the body, that means the momentum of the body is constant. Yes or no? Right. So we can say that if there is no force acting on the body, no force acting on the body, then if there is no force acting on the body, or you can say though no net external force is acting on the body, no net external force is acting on the body, right? Force is acting on the body. That means the momentum of the body is constant, conserved, not changing, right? That then the momentum of the body will not change. I hope the idea is very, very clear. Let's move on and talk about the next part. So the net external force is 0. So that means the net external force is 0. That means there will be no change in the momentum, right? Or the momentum of the body will remain constant. So this is the law of conservation of momentum. Momentum stays conserved, constant, when there is no net external force, right? Simple. So let's talk about the next part. These are the simple things. Here we have 2 billiard balls of mass 0.05 kilograms, each moving in opposite direction with 10 meter per second. There are 2 billiard balls of certain mass. They are moving in opposite directions. So one is moving this way, the other is moving the other way, right? And they are moving with 10 meter per second. They are moving with 10 meter per second. Is anybody pushing them? No. Right? They have the initial kinetic energy, and by using their own energy, they are moving with 10 meter per second towards each other, right? They collide. So when they are colliding, are we taking the body and pushing them towards each other? Are we making them collide? We can say no. Are we making them collide? No. So look at that. Try to understand collision, right? So when two bodies are colliding, this body is moving, it has its own kinetic energy. This body is also moving, it has its own kinetic energy, and both of them are moving on the same line of action. So which is why they are going to collide like this. This has a velocity u1 and this has a velocity u2 before collision, right? So this is the situation before collision. Okay. After collision, what is happening? After collision, the direction of velocity could be anything. Let's say that this is moving in this direction, the other one is moving in that direction with the velocity v1 and v2, right? With the velocity v1 and v2. So now understand that what is happening, right? Before collision, they were moving with u1, u2. Once they collide, and now this body is moving with v1, the other body is moving with v2. Now think about it. In the collision, this body will apply the force on this one. So the momentum of this body will change. Sure. This body is going to apply force on this one. So the momentum of this body will change. But if I talk about the system, this is the entire system. My dear kids, if I look at this colliding particles from here, nobody is applying the force on the system. These bodies inside the system have their own kinetic energy. They move and collide by using their own kinetic energies. So the force acting on the system is 0, right? Individual bodies are colliding, applying force on each other, and individual bodies are changing their momentum, sure. But if I look at the system, the force acting on the system is 0. Nobody is applying the force on the bodies so that they can collide, right? So we can say that if there is no force acting on the body, if there is no force acting on a thing, the momentum of that thing is not going to change. Here, what you have studied in the law of conservation of momentum, right? If there is no force, no net force acting on that particular thing, the momentum of that thing is going to stay constant. Here, no force is acting on the system, right? So momentum of system will remain constant. Momentum of this system stays constant. That means whatever happens inside the system, that cannot change the momentum of the system. So collision is happening, and whatever is happening inside the system, momentum of the system will not change, right? So what is the momentum of the system right now? This one has a mass m1, this one has a mass m2. So momentum of the system itself is m1 u1 plus m2 u2, m1 u1 plus m2 u2 before collision, right? And after collision and all, right, what is the net momentum of the system? It is m1 and it is m2. So it is m1 v1 and m2 v2, right? m1 v1 and m2 v2. So clearly there was no force applied onto the system, which is why the momentum of the system stays constant. So whatever momentum we had initially, the same momentum we will have after that right now. So these two things are going to be same. m1 u1 plus m2 u2 is same as m1 v1 plus m2 v2. This is how you apply the law of conservation of momentum in the collision, right? This is how you apply law of conservation of momentum in this thing, right? I hope the idea is very, very clear. How to approach a physics problem in JEE Advanced? My dear kid, this lecture is not for that, right? This is for grade 11th kids moving to grade 12th. So I could address your question, but not right now. Okay. So let's move on and talk about the next part. Right. So by looking into this thing, nobody is applying the force on the system. So there are two billiard balls. Look at these two billiard balls as a system, right? They are going to collide with each other. This has certain mass, this has certain mass, which is given 0.05, right? So it is 0.05 kilogram. This is 0.05 kilogram. And they are moving and colliding with each other. They rebound with the same speed. So completely elastic collision is happening. They rebound with the same speed. So after collision 10 and 10, after collision also the speed is 10 and 10, right? So then what is the force exerted by one ball onto the other? So we can say that, and this ball will apply force on this one, and this ball will apply force on this one. On the system, no force is applied. So how much force is applied on a particular ball? We can say that the change of momentum of that specific ball, right? So the force applied on any one ball is change of momentum of that ball. So before and after, the momentum was m into v in this direction. After collision, m into v in this direction. So we can say that change in momentum will be final minus initial. If you are calling this direction as positive, so this direction has to be negative. So we can say that it will be 0.05. Final momentum is m into final velocity. Initial momentum is m into initial velocity. M is taken out as common. M was 0.05. And here you have to put the velocities, which is 10 minus 10, right? So basically it is 2mv 0.05 into 20. Just multiply that, right? And you will have your answer. Okay. All right. So this is the change of momentum acting on the body. So once you know the change of momentum, right, now you know that what will be the force required, right? So this is how the force is 1 kilogram per second. So 1 is the answer, right? But my dear kids, they're also asking that if the time duration of the constant is 0.005 seconds, this collision is happening for 0.005 seconds, then what is the force exerted on the ball due to each other? They are talking about the average force basically. So once you have calculated, this is not the force acting on the ball. This is the change of momentum, sorry. This is the change of momentum acting on the ball. This is the change of momentum of a ball. Change of momentum of a ball we have calculated, right? Yeah, so this is one little mistake I had done. So we have calculated the change of momentum of one ball. Now we will calculate the force of that ball, right? So by the impulse momentum equation, why so? Why, sir, this was not the force? Because force is not just the change of momentum. Force is rate of change of momentum, my dear kids, right? Force is rate of change of momentum. So basically, we have just calculated the change of momentum, and we know that the impulse acting on the body is equals to the change of momentum, right? Impulse is average force into the time duration. That is equals to change in momentum. So average force acting on the body, this value is the change in momentum upon the time duration, right? So whatever change in momentum that you have created, that is 1, and time is 0.005. So divide it and you will get the value of average force. I hope the idea is very, very clear, right? You will calculate the value of average force, right? So let's keep on moving and talk about the next part. Right, let's keep on moving and talk about the next part. Okay. Now, let's talk about this free body diagram. What is this free body diagram? My dear kids, in physics, there are multiple instances when one system is made up of multiple subsystems or different bodies, right? We are not interested, let us say that, what will happen to all of the other parts. For example, here, this is the wall, right? And this, from this wall, this is an overhang or cantilever that you have created. On this cantilever, a weight is attached, right? Now, let's say that this is the punching bag that we have attached on this cantilever. We will practice on this thing. So for all meaningful purposes, we don't want this cantilever to break, right? We are now not concerned about the strength of the wall, because the wall can break as well, but we are not talking about that part. We are not interested what will happen with the wall itself, right? We are talking about what is happening with the cantilever, right? So in that situation, or we are also interested in what will happen at this particular point as well, right? So what is the maximum force you can apply over here, and all those calculations we can do, right? And what is the maximum weight of punching bag you can hang from here, right? We can talk about those things. So basically, what are we doing over here? We are interested in a specific system. We are interested in either this cantilever, right? Or we are interested in what is happening at exactly these joints, right? Or we are interested in what is happening at this joint, what is happening with this particular thing. Or similarly, you can have a system of multiple particles, right? For example, you can have a situation like this. A block is there, and that is moving attached with a rope with another mass. This is the frictionless pulley. So clearly, this is going to move like this, and this is going to move like this, right? My dear kids, there are two masses, but in the question they are asking how fast this mass will move. This mass will move after 10 seconds, right? So they are not interested in the velocity or any other parameter of this mass. They are only interested in the parameters of this mass. So what we need to do is, we have to separate this body from the rest of the system, right? So when we separate one body from the rest of the system, we are making it free from the rest of the system. We are calling it the free body diagram. We are calling it a free body diagram. I hope the idea is very, very clear, right? We are calling it the free body diagram. I hope it is making some sense, right? So let's move on. What are the forces that we show while making the free body diagram? We talk about the weight, normal reaction, tension force, friction force, and elastic spring force. All the forces which are acting on the body are shown in the free body diagram when we separate it. Okay. So the weight of the body acts downward like this, m into g, right? Normal reaction is a resultant basically. So what is really happening when two surfaces press against each other, right? So the support you provide is basically the normal reaction. In the layman terms, basically, we can talk, it is an electromagnetic force and all those things, but we are not going into that. Normal reaction is, think about it. Here, this is my hand, right? And this is the box. If I keep this box in the air, this will definitely fall, right? Now think about it. If I push the box with a much higher force, the box will move in the upward direction, right? And if I leave it, it is moving in the downward direction. Let us say that 10 newtons of force is acting downward because of gravity, right? And if I apply 20 newtons of force in the upward direction, so downward is 10 newton, and I'm applying 20 newton, so net force is in the upward direction, the body will move in the upward direction, right? Now think about it. If the downward force is 10 newton and the upward force is also 10 newton, then what will happen with the body? We can say that this body will neither move upward or downward. You see that the gravity is pulling it with 10 newton, and I am also applying the 10 newton on the body. So basically the net force on the body is 0 and the body is not moving. Think about it. Imagine in place of my hand there was a table, right? So a body is placed on the table. The gravity is pulling the body downward with 10 newton on whatever weight of the body is, right? Earth is pulling the body with that 10 newton force is there. And you see that because this particular box is not moving towards the earth, somebody is pushing it upward. What is that? The table is pushing it, applying that 10 newtons in the upward direction, right? And this force is coming due to the contact of two bodies. So we are calling it is a type of a contact force, right? It's a normal contact force. Why? Because it acts always perpendicular to the contact surfaces, right? it always acts perpendicular to the contact surfaces. So right now what is happening? Here we have a block, right? And this is the table. So it could be my hand as well. So right now this box is being pulled towards the earth with the gravity, with the force of 10 newtons, right? But the box is not moving in the direction of force. It is neither moving up or down. So the net force must be 0. So somebody is applying the force on the block. So this is the contact surface, and the table is applying the force on the block, right, of the same value in the upward direction. So on the block, the same force is acting upward and downward. This is why the net force is 0 and the block doesn't move. So clearly, the table is supporting the block with the application of this normal reaction or normal force. So when this force acts, when two surfaces press against each other, the normal reaction acts. The lesser they push against each other, the lesser is the value of normal reaction. Understand this way? Right. Here I have this surface, right? And if I push, if I put this body, let's say that this body on this surface, right now, the weight of this body is being pushed against the surface, so it is getting the normal reaction. Now think about it. Now all of the weight is not pushing against the surface. You see that the body has a tendency to move forward. So only a component of weight is pushing against the surface, and a component of weight. Now the surface is not pushing harder right now. Right now the surface is this box is pushing harder against the surface. Now the box is not pushing as hard against the surface. If I tilt it further at this angle, the box doesn't even want to push against the surface. It wants to slide down, right? Yes or no? Clear? So the tendency to push against the surface is reducing, and that reduction in tendency to push against the surface is causing the drop of normal reaction, right? So I hope you have understood. Normal reaction is governed by how hard the two surfaces press against each other, right? The surface is flat and the box is there. Now all of the weight is pushing against the surface, right? Pushing against the ground, right? So the normal reaction is going to be maximum, which is going to be equals to the weight. But if I have this angle, theta, so the weight is like this. Weight is W or mg, right? This angle is theta. This is W cos theta. And this is W sin theta. Think about this component W sin theta. This component is not interested to push against the surface, right? This is interested in moving the body along the plane. So right now, instead of entire weight, only a component of weight W cos theta is pushing. If theta, let us say, is 60, so it is W into cos 60, which is 1 by 2. So it is W by 2. W into cos 60. So it is W by 2. Cos 60 is 1 upon 2, right? So here, all of the weight was pushing against the surface and the normal reaction was equals to the weight. Here, only a part of the weight is pushing against the surface. So normal reaction is against this much, right? Against this much, right? Which is normal reaction is equals to W by 2. So normal reaction has reduced. So if you keep on increasing the angle and you make the theta 90 degree, so the normal reaction will become cos 90, which is 0. So basically the surface is not offering any support, right? I hope the idea is very, very clear, right? In which case the normal reaction acts, we can say that when the surface wants to support when the two surfaces wants to support each other, or when two surfaces are pressing against each other, in those situations the normal reaction is there, otherwise it is not there. Now let us move and talk about the tension force. Again, a very, very important thing to understand. Tension force. Many times kids are confused, sir, why whenever a force is acting on a body, it is always shown with one direction, right? Like this will be the direction of tension force, but tension force is shown multiple times like this arrow. So how can a single force, tension force, has two directions at the same time? How come the tension force has two directions at the same time? This is the confusion, right? What is the direction of tension force? Understand that. Imagine this is the support from where a rope is hanging, and on that rope a mass is attached. Now think about it. Because of the mass is being pulled towards the earth with a weight mg, right? What is happening with the rope? The support is holding the rope wherever it is, and this end is pulling it in this way. So you see that what is really happening? What is really happening? These arrows, I'm not representing the direction of force acting on the rope. Understand that. The rope is, let's say, inextensible. The rope is inextensible, but for this moment, the rope cannot be extended for all the purposes that we deal. But for right now, imagine instead of this rope, we had a rubber band, right? And instead of this wall, we have another hand. So if I'm holding, let's say like this, right? So I'm holding this thing, this rope over here. So what is really happening? What is really happening? The weight is acting downward. So you see that this hand is trying to lift it, right? And this hand, this weight is, pulling it downward, right? So what is really happening with this thing? This end is being pulled in the downward direction. Okay. You see, this end with this weight, this end is pulled in the downward direction like this, right? And what is really happening in this place, right? Because the weight of this block is being pulled downward, so the rope is trying to pull it back like this. Imagine a spring, right? So when you try to stretch the spring is, attracting. Imagine that this is the spring and you're trying to stretch the spring like this. So look at that. This hand wants to go here and this hand wants to go here, right? And instead of a spring, now imagine a rope. When I'm trying to stretch the rope, this hand wants to go back and this hand also wants to go back, right? So whatever we attach at the ends of the rope is applying the force on those two objects in this direction, right? In this direction like this. So the rope, these are the directions applied by the tension created in the rope on the objects connected at the end. This is not the direction of force acting on the rope. These are the directions. These are the direction of the force applied by the rope. Force applied by the rope. Applied by the rope on the objects connected at the ends. At the ends. I hope the idea is very, very clear, right? Direction of the force applied by the rope on the objects connected at the end, right? So here you can clearly say that this end, this object is experiencing a tension force in this direction and the upper end is experiencing the tension force in the downward direction, right? I hope the idea is very, very clear. Okay. So let's keep on moving and talk about this idea. I hope everybody is clear with this thing, right? Why we are showing the two direction of tension force. This is not the two direction of tension force. This is showing the direction of forces applied on the object connected at the end of the rope, right? So this is, I believe these arrows are now very clear. This is how the tension in the rope will act on the object number 1, and this is how the tension on the object 2 will act. I believe the idea is very clear, right? Okay. Now let's move on and talk about the next idea. Friction force. Friction force is again very, very clear. Friction is, we will discuss the frictional force in a great detail in upcoming pages. However, the frictional force opposes the tendency of motion or the actual motion. So this body is experiencing a force this way. The friction force on the surface of the body is acting this way, and on the ground, the friction force is the opposite way. Elastic spring force. So spring force, if you stretch a spring wants to restore itself, right? That restoring force is called as the elastic spring force. So this is the fixed ground. This is the spring. And if you attach a mass over here, so it will pull the string like this, right? By some amount, delta x. It will stretch it by some amount. Whatever stretch you have created, it will try to create a restoring force based on that. So if you stretch it by x amount, it will increase the force, right? The restoring force will increase. But the direction of restoring force is opposite to the direction of stretch. You are stretching it in this direction. The restoring force is in the opposite direction. So there is a minus sign, right? So if you remove that minus sign, so F is equals to minus kx, right? So the translational equilibrium, I have already discussed. The translational equilibrium when there is no linear acceleration. Right? There is no linear acceleration. That means there is no net force. Now let us discuss this part as well. Right? Now let us discuss this part as well. Here what is happening? there are two masses experiencing a force F, right? So if you want to draw the free body diagram of individual bodies, right? Let's say that they are asking what will be the contact force acting on the second mass. So for that, we have to analyze the second mass separately, right? So what is really happening? There are two blocks placed against each other. So when you apply force here, some of the force is transferred onto the second body, right? So if they are asking what is the force transfer to the second body, then we have to deal with the FBD of individual bodies. So how will you deal that? So how will you make that? M1 and M2, they are separated. M1 and M2, they are separated. My dear kids, this force is acting on the body M1, right? And in between them, there will be only normal reaction. So the normal reaction on this body is in this direction, and on this one it is this direction, and this is same. Normal reaction is same on these two bodies, right? So at this interface, the normal reaction is going to be same, right? Now, this whole thing is going to have a common acceleration, right? The whole thing will have a common acceleration. So this one has acceleration A, and this one also has acceleration A. Now, when you apply Newton's second law, net force F minus N is equals to mass into acceleration M1 into A. And net force here, N, is equals to M2 into A. I hope the idea is very, very clear. Whenever you draw the free body diagram of anything, must use the acceleration as well, right? Okay. So there are three bodies right now. So clearly three bodies are there. So there are two interface over here, right? So at this particular place, the normal reaction is N1. And at this place, the normal reaction is going to be N2, right? So yeah, we can go ahead and solve it. All right. So look into this question. There are two blocks, 4 and 6 kg. They are placed in contact with each other, right, on a frictionless horizontal surface. If we apply a push of 5 Newton on the heavier mass, which is the heavier mass, the force on the lighter mass will be, how much force will be transferred on this one, which is the normal reaction they are asking. The whole system will move with a common acceleration A because there is a force acting on both the blocks. So the acceleration of this whole thing will be net force upon total mass, M1 plus M2. Net force is, 5 Newton. The force acting here is 5 Newton. And the masses are 4 kilograms and 6 kilograms, which is 10 kilograms. So 0.5 meter per second square. That will be the acceleration of a body. Once you know the acceleration, you can look at individual bodies. So think about the FBD of this smaller block. So the normal reaction is acting over here and it is accelerating with acceleration A. So mass of the smaller block is 4 kilograms, right? Mass of the smaller block is going to be the 4 kilograms, right? Like this. So mass into acceleration is 0.5 is the normal reaction over here. So it is going to be 2 newtons, right? So option C is the correct option, right? Now, similarly, when two bodies are connected with a string, right? Two bodies are connected with a string and you are pulling them forward like this. So they will also share the same acceleration, and acceleration will be net pulling force upon total mass. Acceleration will be net pulling force upon total mass. I hope that is very, very clear, right? Now, there are three blocks of 2, 3 and 5 kilograms. They are connected to each other with light string and then placed on a frictionless surface as shown in the figure. The system is pulled by the force of 10 Newton. Then what will be the tension T1? Okay, so we have to talk about the tension T1. Right, let's say that tension here is T1, tension here is T2. We are applying a force of how much? We are applying a force of 10 Newton, right? The masses are 2 kilogram, 3 kilogram and 5 kilogram. Okay, so what will be the tension, or you can say what will be the acceleration of the common acceleration of the system? We can say acceleration of the system will be net pulling force upon total mass, which is 2, 3 and 5. So 5, 3, 8, 8 and 2, 10. So acceleration is 1 meter per second square. Now what you can do, look at the FBD of anything. For example, you can look at the FBD of this block. It is experiencing a force of 10 Newton this way. It is experiencing a tension force T1 this way. And it is experiencing an acceleration in this direction, which is 1 meter per second square. So by looking at the FBD, we can say that 10 minus T1 is mass, which is 2 kilogram, into acceleration. So T1 is equals to 10 minus 2 or 8 Newton. So option C is correct. All right. So same thing is applied on a pulley block system as well. So if you have a simple pulley, it is called as Atwood's machine as well, right? So this one is moving. This one has mass m1. This one has mass m2. If m2 is higher, the m1 will move up and m2 will move down, as obvious as it sounds, right? So the net pulling force will be m2a minus m2g minus m1g, right? So the net pulling force upon total mass will be the common acceleration of the system. And again, rest of the things are same, right? Now let us discuss the friction, and then we will move on and talk about the next part, which is the concept of work, power, and energy. All right, just a second. All right. Now, friction is a force that opposes the relative motion between two surfaces. What is friction? Friction is a force that opposes. The nature of friction is such that friction opposes the relative motion between two surfaces. Right? Friction opposes the relative motion between two surfaces, right? Or they might not have actual relative motion. For example, this is one surface and this is another surface, right? Okay. What is relative motion, by the way? These are two surfaces, right? These are two surfaces. One surface is this, other surface is this, right? And the whole thing is moving. So the whole thing is under motion, but there is no relative motion between the surfaces. We are not going to talk about the friction right now, right? Friction is only applicable when there is a relative motion between the surfaces. When there is a relative motion between the surfaces, basically like this. So two surfaces must rub against each other for the friction to act. Okay. So it is also possible this surface is stationary and the other one is moving like this, sliding like this, right? Okay. Now in the books we have seen the friction force acts in two situations. Either the two surfaces have the relative motion or there is a tendency of relative motion. My dear kids, one thing is very clear, that how to perceive a relative motion. Perceiving relative motion is clear. How to perceive the tendency of relative motion? So tendency of relative motion is there. Understand? Imagine I'm applying a very small force on a upper block. The lower block is stationary, and applying a, let's say, 1 Newton force on the upper block, and the block is not moving. Because of the rough surfaces in contact, the whole thing is stationary. Okay. I'm applying 2 Newton, the block is not moving. I'm applying 3 Newton, the block is not moving. I'm applying 4, not moving. 5, not moving. But as soon as I started applying 5.1 Newton, more than 5, the block just starts to slide, right? So right now we can say that till 5 Newton, there was force acting on the body and there was no relative motion. But since there was a force, there was a tendency of relative motion this way, right? And in that situation, the friction that was stopping was called as static friction, right? So my dear kids, it is not that the static friction means two rough surfaces are in contact and there is a static friction. No. Static friction acts when there is a tendency of relative motion between two surfaces, right? So friction opposes the relative motion or the tendency of relative motion, you can say. Actual relative motion or tendency of relative motion between two surfaces, right? So now we can say that if this particular body is there and the surface is rough, and here we have another surface which is also rough, two rough surfaces are in contact, will there be any static friction? Surfaces are stationary, will there be any static friction? We can say no. Right now there is no static friction. Right now there is no static friction. When will you say that there will be static friction, right? When you apply a force on this body And even if you have applied the force on the body, there is no motion, right? My dear kids, the force is applied, but the motion is not there. That means something is opposing you. And that, my dear kids, is the static friction. So static friction is opposing the tendency of relative motion, right? Static friction opposes the tendency of relative motion between two surfaces, right? Okay. The static friction opposes the tendency of relative motion between two surfaces, right? Okay. All right. And how will you get that tendency? When there is a net force acting on the body. If you remove the external force, if the external force acting on the zero, that means if you remove the external force, the body has no tendency to move. The body is rough, making a contact with another rough surface, but it has no tendency to move, right? And once a small force is acting, but the body is not moving, there is a tendency of motion and the static friction is there, right? So this is what we have seen. Maximum value of static friction that can act between the two surfaces is called as limiting static friction, right? Okay, or limiting friction. I hope the idea is very, very clear. So limiting friction is mu s into n. Limiting friction is mu s into n. Shivani, okay, right. Limiting friction is mu s into n. All right. So you see that. How will you understand the limiting friction? This is a rough surface. This is another rough surface in contact. Right now, the two surfaces are rough but placed against each other. The bodies are stationary. Is there any static friction? No. You apply the external force. Right now the external force is of 2 Newton, let us say, right? So the static friction is not constant between two rough surfaces. It changes, right? Now think about it. If the static surface friction between these two surfaces were always constant, let us say that static friction is 10 Newton. And right now, the 10 Newton static friction is acting on the block. You see, you are applying 2 Newton and the static friction is 10 Newton. So effectively, there is 10 minus 2, 8 Newton force is there. And effectively, the 8 Newton force will move the body in this direction. So you are applying 2 Newton and the body is moving with the net force of 8 Newton, which is not possible, right? Nature cannot go against itself, right? So we can say that if you are applying 2 Newton and the body is not moving, that means it is only opposing you with 2 Newton. You apply 3, you will be opposed by 3. You apply 4, you will be opposed by 4, right? Gradually, the maximum value of friction that can be applied by the surface contact surfaces is called as limiting value of static friction. Limiting value of static friction, which is mu s, coefficient of static friction, into the normal reaction, right? Coefficient of static friction into the normal reaction. Let us say that the mass of this block is 1 kilogram. Let us say that the mass of this block is 1 kilogram. So the normal reaction is going to be equals to the weight, right? Normal reaction will be equals to the weight. And let's say the coefficient of static friction between these two surfaces is 1.7. Okay. So 1.7 into m into g, which is 17 Newton. So the maximum static friction which can act between this surface and the body and the ground is 17 Newton, right? So you can continue to keep on increasing, right, the force. Let's say you are applying a force of 16 Newton. Now you will be opposed by 16 Newton. You see that the maximum possible value is 17. Understand that between these two surfaces, the maximum static friction is mu s into n. It is not acting all the time, right? Let us say in the question they are telling you, on this body a force of 10 Newton is acting. On this body of mass 1 kilogram, right, and static friction coefficient is given, which is 1.7 between the surfaces, and they are telling you a 10 Newton force is acting on the body. So you have to tell what will be the static friction right now. So my dear kids, if you are applying with 10 Newton, first of all calculate what is the maximum possible value. The maximum possible static friction is 17 Newton over here, right? So will you get 17 Newton of static friction all the time? No. Because if all of the 17 Newton will act and you are applying only 10, so that effectively 7 Newton of net force will be acting on the body and will move it, which is not possible. The body is moving because of friction. No, it's not possible. So we can say that right now 17 Newton is the maximum possible values, but out of that 17, only how much will act? 10 is only going to act because you are applying 10 on this side, right? So whenever the external force is less than the limiting friction, then the value of static friction that acts is always same as the external force, right? So if the external force is less than the limiting friction is 17. So static friction that will be acting between the surfaces will be equal to the external force, right? Okay, I hope the idea is very, very clear. Right, let's move on and talk about the next idea. Kinetic friction, once the body crosses the limit of limiting friction, then the body starts moving, right? And in that situation, we are talking about kinetic friction. In that situation, we are talking about the kinetic friction, which is mu k into n. Okay, mu k is coefficient of kinetic friction, right? Coefficient of kinetic friction. I hope that is very, very clear. Right. So you see that the static friction continuously increases, and there is a little bump, and then there is kinetic friction. So you see that the maximum value of static friction or the limiting friction is higher than the kinetic friction in general, right? So angle of friction, now let us talk about that. So angle of friction is the resultant of F and N, right? So angle of friction is the resultant of normal reaction and the friction force. Yeah, angle of repose is a good concept. Let's understand that. Angle of repose is something that helps us to calculate the coefficient of static friction between the two surfaces, right? So here we have a wooden plank, and here I have a plastic box. I want to both are rough surfaces. I want to calculate what will be the coefficient of static friction between these two surfaces, right? What will I do? I will place one over the other, and I will try to measure the angle of this plank from the surface. I am tilting it, right now the angle, let us say, is 10 degree. At 20 it is not sliding on its own. At 30 it is not sliding. At 35 it is not sliding. At 40 it just starts to slide, right? So when the angle between the angle made by the surface is 40 degrees, without any application of my interference, the body started to slide, so that became the angle of repose for this particular pair, right? So at theta, the body will start to slide. That is the angle of repose over here. Once you know the angle of repose, take the tan of angle of repose. This, for example, in 40 degree, the block was sliding, right? So tan of 40 degree will give you the coefficient of static friction between the block and the metal surface, block and the wooden surface, right? So here it is. So if theta naught is the angle at which it starts to slide, right? So here we can say that mu s is tan theta. Coefficient of static friction is tan of angle of repose. That's how you can calculate. All right. Now let us discuss the second part of the chapter, second part of the session, which is work, energy, and power, right? So the concept of work will be discussed, concepts of energy will be discussed, and then the concept of power will be discussed, right? Okay. So just take a break of 1 minute or so, and then we will continue with this work, energy, and power thing, right? So this is the syllabus of this thing we will be discussing just in a minute. Okay. So just let me have some water. All right, so let's continue and start talking about this particular part. Okay. So we are discussing this chapter called as work, energy and power. We are discussing this chapter called as work, energy and power. Okay. And here we have it. So we have the idea of work done by a constant force and a work done by the variable force. Then we have the concept of kinetic and potential energy. And finally, the concept of power we have, right? So let us discuss everything step by step manner, right? These are all the topics. We'll be talking about that, right? So work done by the constant force. This is what we have studied in grade 9th as well. If a constant force is acting on the body, it displaces the body from the initial place to that another new place. The displacement is d. Then the work done will be Fd. If the force is making an angle with a displacement theta, so work done will be Fd cos theta, right? In this formula, we can put one value of force, right? We cannot put, let's say that during the journey from here to here, the force changes. Right now the force is 5 Newton, the next second force is 10 Newton, the next second force is 15 Newton. If the force itself is changing during the displacement, so you will put the displacement d, but what will be the value of force that you're going to use? We cannot use it, right? So if the force is changing, this formula is not going to be useful. This is only useful when the force is stationary. Okay, force is constant, sorry, right? So yeah, all right. So when the force and displacement have this angle less than 90 degrees, so basically positive work is when the force tries to increase the kinetic energy, when the work tries to increase the kinetic energy of the body, will make it faster, right? Positive work. And negative work will be when the work done by the force is such, it wants to slow it down. For example, friction, right? When the body is moving, the friction force is acting in the entire journey, but it is trying to slow down the body. So the work done by the friction will come out to be negative, right? So in this situation, for example, you see that there is one component of force which is perpendicular, it will not do any work, and another component of force which is acting opposite to the displacement. So it will try to slow down the body, right? So it will do the negative work, right? So zero work when there is no displacement caused by the force, there is zero work. So here you are pushing against the wall, no work will be done. Or the work and displacement have the force and displacements have an angle of 90 degree, then in that situation the work done by that particular force during the displacement will be zero. Here the planet is moving around an object is moving around the planet. So you see that, look at this force, right? Look at any in this particular situation, the displacement is happening in this direction. This is the direction of displacement, and this is the direction of force, centripetal force, right? Look at that. In the displacement, the angle between the displacement and the force is 90 degree. So centripetal force is not doing any work in this rotational part, right? Now let us talk about the work done by the variable force. So the force is changing as the body moves in the x direction, right? Right. So the force is changing as the body moves in the forward direction. Okay. So in that situation, what will happen? We will take the area under the curve, right? We will say that there is a small segment dx, right? And the force acting in that duration is F. So what will be the value of work done in that little segment? So it will be F into dx in that little segment. And if you integrate it from initial position xi to the final position xf, so basically you are calculating how much work will be done in these two limits. So you can do so by integrating between xi to xf. Basically that expression is telling you the area under the fx curve, area under the force displacement curve from xi, initial position to final position. So from initial position to final position, the area under the curve is basically telling you this thing, all right? Work done by this variable force. I hope that is very, very clear. Let's keep on moving. Work done by the spring force. So here we have the work done by the spring force. All right. So how much force is there acting applied by the spring? You can say that if you are displacing it by the x displacement, the restoring force will be kx, right? And work done by the spring force is going to be integration of kx into dx. So if you integrate the kx, it will be kx square by 2 or half kx square. So this is the work done by the spring, and that will be stored in the potential energy of the spring, right? We will talk about that part. Work done by the gravitational force. So if you are lifting the body against the gravity so that it does not accelerate, right? You're moving it like this, right? So what will happen? The force is equals to mg in that situation because we are not trying it to accelerate, right? So in that situation, how much work is done against gravity? So it is mg into h into cos of 180. So it is mgh, right? So that much work is basically stored in the body again. Is stored in the system, I should say, system, not just the body, right? In the form of energy. So work done by variable force we have calculated already, right? So work done by variable force, this expression of integral of fx dx, right? This is telling us the area under the fx curve, right? In that situation. Look at that. Force is this 10I, 3J, 6K acts on a body of 5 kilogram and displaces it from this place to that place. What will be the value of work done? Here we have a constant force, right? But here the work done is F vector dot displacement vector. So what will be the force vector over here? So the force vector over here is 10I, 3J and 6K. And displacement vector is, it is moving from A to B. So displacement will be the position vector of B minus position vector of A. So 10I minus 6I is 4I. 2J minus 5K is minus 7K, 7J. 7K minus 3K, right? So it is plus 10K. Let's confirm it once, right? So we are moving from A to B. So position vector of B minus position vector of A, that is a displacement, right? So position vector of B minus position vector of A. So that is 10I minus 6I, 4I. So here minus 2J minus 5J, it is minus 7J. 7K minus 3K, it is plus 10K. I hope the idea is very, very clear. So the work done is just the dot product of these two things. You know, take 10 with 4, it is 40. Take minus 3 with this thing, it is plus 21. Take 6 with this 3, plus 60. Right, just add it out and you will have your final answer. 121, yeah. Right. Similarly, the work done by the force is displacing a particle from x4 to x minus 2. So here we have a variable force. How much work will be done by the variable force? Integrate it, f dx, from where? From x equals to 4 to x equals to minus 2. So just integrate it. All right. Integration of x cube is x to the power 4 upon 4. Lower limit is 4, upper limit is minus 2. Put upper limit minus lower limit and that will be your solution, right? So do the calculation part yourself. Okay. A block of mass 10 kg is moving along x-axis under the action of force 5x Newton. The work done by the force in moving the block from 2 to 4 will be. So force is this, which is the variable force, depends on x. So work done by such a force will be fx dx, right? So it is moving from 2 meters to 4 meters. We have x square by 2. So put upper limit minus lower limit and that is going to be your answer, right? So not very difficult. So force is this, displacing from 2 to 4. What will be the work done? Again, the same formula, integrate it and put the limits. All right. Now let us talk about the concept of kinetic energy. The concept of kinetic energy is same, right? The concept of kinetic energy is very, very easy, right? The concept of kinetic energy is very, very easy. Okay. Okay. So if a mass m is moving with velocity v, the kinetic energy contained by the body will be half mv square, right? The kinetic energy contained in the body will be half mv square, right? Now, there are multiple instances because kinetic energy depends on mass and velocity. And there is one more quantity which is vector quantity, but also depends on mass and velocity. Kinetic energy depending on mass and speed, I should say, right? So we can relate these two things, right? Momentum is mass times velocity. Kinetic energy is half mv square. So if I do that, half m square v square upon m. So in place of this, we can put a square of momentum upon twice of mass. right? So this is how the kinetic energy can be written. The square of momentum upon twice of mass, right? Multiple times it is used. And the previous year NEET papers, this is asked various times, right? Okay. Look at this question. A man has a box of weight 10 kilogram. So basically they are giving the mass, not the weight. 10 kilograms. The energy of the box when the man runs with a constant velocity of 2 meters per second along the box with behind the bus is. So what will be the energy? The velocity is 2 meters per second. So the kinetic energy will be half mv square. Half mv square. Solve it is 20 joule. Option C. We have that much mass, velocity is this, at a certain instant kinetic energy of kinetic energy at that instant is going to be. So what will be the kinetic energy? So right now for the kinetic energy you need half mass and magnitude of velocity, which is speed, right? So speed is given in the velocity is given in the vector format. So magnitude of velocity will be under root this is square and this is square. So 4 and 25 under root 29. Okay. So a square of under root 29, mass is 120 grams, okay? And under root 29 square is only 29. Just multiply it and you'll have your answer. Two solids A and B of mass 1 and 2 kilogram respectively moving with equal linear momentum, right? The ratio of their kinetic energy will be A is to 1. So the value of A will be, right? Two solids A and B of mass 1 kg and 2 kg respectively are moving with equal linear momentum, right? So we have two bodies are moving with equal linear momentum, right? So the linear momentum of A is same as linear momentum of B, okay? The masses are different, right? So we can say that MA and VA is same as MB and VB. Right, masses are not same. MA is 1 kg and MB is 2 kg. So we have VA is equals to 2 times VB, right? Okay. The ratio of their kinetic energy will be A is to 1, right? So what is the value of A? Very simple, right? There are multiple ways you can solve it. Very simple kind of problem is there. So we have kinetic energy of A and kinetic energy of B. So it is half m A VA square and half m B VB square, right? So MA upon MB is 1 is to 2, right? And VA upon VB is 2 is to 1. So square of that is 2 square upon 1 square. So 2 is to 1 will be the final answer. Ratio of kinetic energy will be 2 is to 1. Now the next thing is work energy theorem. Work energy theorem is telling you that the work done by all the forces acting on the body will be equal to the change of kinetic energy that we are bringing upon it, right? So work done by all the forces acting on the body is equal to change of kinetic energy. All right. So a particle of mass 0.1 kilogram is subjected to a force which varies with distance as shown in the figure, right? This is how the situation is. If it starts its journey from rest at x equals to 0, its velocity at x equals to 12 will be. What will be the velocity at x equals to 12? My dear kids, the work energy theorem is simply telling you whatever work you have done will reflect in a form of change in the kinetic energy. If you have done 200 joules of work, the kinetic energy of the body should ideally increase by 200 joules, right? So here what is happening? In this particular situation, the force is clearly changing with the displacement. So it's a variable force. But if you can calculate the area under the curve, it will give you the work done, right? And you know that the work done is basically the change of kinetic energy, right? And initially it starts from rest, right? The particle is moving like that. So if it starts a journey from rest, so initial velocity is 0, initial kinetic energy is 0, and they are asking what will be the velocity at 12 meter per second. So final kinetic energy, change in kinetic energy, kf minus ki, initial kinetic energy is 0, that is equals to the work done, which is the area under the curve. Area under the curve, right? So area under the curve is area of this trapezium, which is area of this trapezium, or if you don't know the area of trapezium, you can add the triangles with the area of this rectangle, right? So what is the area of trapezium? 1/2 summation of parallel sides, which is this. From here to here it is 4. From here to here it is 12. So 4 plus 12 into the distance between them, right? So it is 10 units. So you calculate the area, you will get the kinetic energy, final kinetic energy, which is half mv square, right? And from here you can get the final velocity as well, right? No worries about that. So this is it. So here you see that the net work done equals to change of kinetic energy, which is this. This initial value is 0, right? And this is the area. 1 upon 2 summation of parallel sides, the area of trapezium, into the distance between them is 10. Right, area equals to change of kinetic energy, which is half mv square, right? So v you can get from here is 40, right? Now the next thing is conservative force. So the name suggests the conservative forces are something that remains conserved, right? Conservative forces are something that remains conserved, right? So what do you mean by that? Okay, my dear kids, here, if imagine I have a spring like this, right? And if I try to compress the spring, I'll be working against the spring restoring forces, right? But whatever work I have done, that is not wasted. That is stored in the spring and hand system. In the system, the energy is stored. If I take this body, right? If I take this body from here to here, right? I have worked against gravity, but that work is not wasted. It is stored in the system, and because of which, if I leave it, it will automatically drop, and the work will be done by the energy stored in the system. So there are multiple instances, right? Or multiple fields, for example, a gravitational field and magnetic field and electrostatic field, in which work done gets is stored in the system in some way or the other, right? So we are dealing with conservative fields in those situations, and the conservative force is the force involved in those situations, right? The work done by the conservative force is independent of the path. For example, if you take the body like this on this path, right, or you take it directly from here to here, the work done against the gravity is still same, because gravity is a conservative force. The work done by the conservative force is not dependent on path, right? It depends on the displacement though, right? And again, if you come back to the same place, the work done in the cycle will become 0 by the conservative force, right? Okay. The non-conservative force, however, has a nature to waste the energy, right? Conservative forces have a nature to preserve the energy, right? Non-conservative forces have a nature to waste the energy. So for example, when the chalk is being rubbed against the blackboard, the chalk is reducing its length, right? So you see that whatever work is done by the friction force, that is wasted to reduce the length of the chalk in rubbing it, right? Similarly, when you take the book on the table in this path and this path, the friction force is doing the work along a larger path and along the smaller path, but the work done by the friction depends on the path taken. Here friction has done the longer work. For that, just to get the feeling of that, you can take a chalk on the table and move it like this. It will reduce more of its length compared to this path, right? Okay. And again, if you take a closed loop with a chalk, again the sum of the length of the chalk will get reduced. The friction is doing some work, right? So in a closed loop, work done by the non-conservative force is not 0. Now the energy is there, right? There are different forms of energy. Energy is the ability of the body to do some work, right? Ability of the system, basically, we can say, to do some work. Lot of different forms of energy. We are not interested in all of them. We are interested in mechanical energy. Mechanical energy means potential and kinetic energies we are interested in, right? So potential energy is the energy stored in the body. For example, these are the toys. When you use the key and store the energy, twist the key, some of the energy is stored in the spring of that particular thing, right? So potential energy is basically equals to the work that you have done, right? Okay. So if the force varies with one dimension, right? So the force is equals to rate of change of potential energy with x, right? Okay. Gravitational potential energy is there, mgh upon 1 plus h per r. This is that. So that is something we'll be discussing in detail in the gravitation chapter. All right. So now you look at this thing. The potential energy and the kinetic energy of the helicopter flying at horizontally at a height of 400 meter are in the ratio of 5:2. So the potential energy and kinetic energy are in the ratio of 5:2. What will be the velocity of helicopter? So my dear kids, it is telling you that the helicopter is flying at a height of 400 meter. So clearly the potential energy of the helicopter can be figured out, right? It is mgh, right? And now the potential energy and the kinetic energy, the ratio of the kinetic energy over here is half mv square is 5:2, right? So we have to tell the velocity. So this and this is cancelled out. The value of g can be taken as 10. 2 will go up, right? And the velocity can be figured out from here, right? No need to worry about that. The spring constant is 8, has an extension of 5. The minimum work done in Joule in increasing the extension from 5 to 15. So basically, we can say the work done is half kx2 square minus x1 square. Yes or no? Half kx2 square is the energy stored after the extension of x2. Kx1 square is the energy stored when you extend it till x1. When you subtract these, you have the difference of energy. So whatever difference of energy is there, that is equal to the work done, right? So the minimum work done is required in this situation. So x2 is given, x1 is given, and k is given. You can simply calculate the work done. Just put the values and get the answer. So k is given, x2 is given, x1 is given. So yeah, simple numerical. Now let's talk about the power. Power is the rate at which the work is being done, right? Or the energy can be consumed. What is power? Power is simply the rate at which the work is done or the energy is consumed, right? Okay. Power is simply the rate at which the work is done or the energy is consumed, right? So work done per unit time, that rate at which the work is done is power, okay? Now, if you put work done is equals to force into displacement, you can get displacement upon time, rate of change of displacement, ds upon dt. Rate of change of displacement is velocity. So instantaneous power is force into velocity vector. Instantaneous power is force into velocity vector. If you are going to prepare for NEET exam, my dear kids, this particular question is going to be, this particular numeric format is going to be very, very useful. Okay. All right. So power is W upon T, mgh upon T. Yeah. Look at that. Power applied to a particle varies with this relation. P is equals to 3t square minus t plus 1. Where t is in second. Find the change in the kinetic energy between the 2 seconds and 4 seconds. So power is given. And with the help of this expression, we have to calculate the change in kinetic energy. Change in kinetic energy between 2 seconds to 4 seconds. Think about it and try to solve it. Yeah, good evening, beta. Think about it and try to solve it. You can have 1 minute. It's a slightly good numerical. That is why I'm giving you some time. Okay. Think about it and try to solve it. Right now, I've just explained you the power is related to that force into velocity vector. And over here, we have seen power is nothing but rate of work done, right? So by looking at those expressions, we can easily solve it. Most important parts are done. Think about it. Work energy. Think in terms of work energy theorem, right? You can solve it. Power is given, my dear kids, 3t square minus t plus 1, right? This is how the power is given, right? And you want to know what will be the change in its kinetic energy. They are not asking about what will be the final velocity and all. They are asking about change in the kinetic energy, right, in this situation, in a certain value, right? Think about it. Let me give you a little hint. You see that power is rate of change of work done, dw by dt. We are interested in kinetic energy change. The change of kinetic energy dependent on work done, right? So somehow if we can relate this power with work done, we can get our problem solved, right? Okay. So you see that dw is equals to p dt, all right? dw is p dt. In a certain interval, how much change of work, how much work will be required? We can say that integral of, if you integrate it for this duration, t is equals to t to 4, you will have the change amount of work required for this specific change. And you know that by work energy theorem, whatever work you have required, that is equals to the change of kinetic energy. That's it. That was the entire concept. The change of kinetic energy is integral t to 4 p dt. T is already given 3t square minus t plus 1. T is equals to t to 4, right? And when you solve it, it will come out to be 3t cube by 3 minus t square by 2 plus t. Lower limit and upper limit. Just put the lower and upper limits and you will get your answer. Change of kinetic energy. All right. So now let's move on and talk about the next part. Efficiency. Efficiency is simply the output upon input, right? Okay, and collisions we have already discussed, but let us have a brief discussion about the collision as well, and then call it tata bye-bye. Okay. All right. So there are different types of collision that we can get, my dear kids. The first type of collision that can happen between the two bodies is the elastic collision. The second type of collision that can happen between two bodies is the inelastic collision. Understand that. If two bodies are, if I have this body and if I want to deform it, if I want to change the shape of this body, I have to apply some force, right? I have to invest some of my energy, okay? Imagine that this body is moving. So right now it has kinetic energy because it is moving. It has certain mass, it has certain velocity, it has kinetic energy, right? It is hitting against this another ball. Imagine that, right? Both of these balls get no change in the shape. So both of them maintain the exact same shape, right? Like two billiard balls. We can consider this collision to be fairly elastic because no part of their energies is wasted to deform them. But imagine if one of these balls is made up of clay, right? And now they are moving. Think about it. The system had some kinetic energy. Think about it. Right now, let us say that it has 10 joules of kinetic energy. It has 20 joule of kinetic energy when they are moving, right? But when they collide, a part of the kinetic energy will be wasted in deforming this clay ball. Yes or no? So this collision, in this collision, the total kinetic energy of the system will not remain constant, right? Right now it is 10 plus 20, 30 joule. The system has 30 joule of kinetic energy. But after the collision, a part of that 30 joule will be wasted to deform it, right? So right now we can say that this collision is not an elastic collision. It is inelastic because a part of the system's kinetic energy is wasted in the deformation. All right. All right. Okay. I hope that is very, very clear. The next part is perfectly inelastic collision. Perfectly inelastic means what is really happening? Let's say that if two bodies collide in such a way, for example, you throw a clay ball on a moving truck, it will not happen more or less that the clay ball is going to strike the truck and bounce back. It will more or less will stuck to the stuck to the truck and move along with the truck ahead. Yes or no? So what will happen? What will happen in this situation? If two bodies collide in such a way that after the collision they become one and they move together, so that is the perfectly inelastic collision, right? Okay. So right now you see that if the collision is perfectly elastic, the ball will bounce off the surface and rise to the same level. If it is inelastic, so some of the energy will be lost, right, in the collision, and it will not rise to the same level. Okay, and yeah, and if it is perfectly inelastic, it will stick to the ground. Okay, and on the basis of direction, how many types of collision we have? One dimensional collision and two dimensional collision. So in one dimensional collision, there is one line of action along which the bodies are moving before collision, and the bodies continue to move along the same line of action. The direction can change, right, but they always move along the same line of action, right? But on this situation, on the second case, in the oblique collision, this body has a different line of action, the other body has a different line of action, right, or you can say direction of motion. So when they collide, after collision they can have different velocities again, right? So this is an oblique collision, right? Now there is a term called coefficient of restitution. It is simply the velocity of separation upon velocity of approach, right? Okay, so Newton, did a lot of experiments on different bodies, calculated the coefficient of restitution for different bodies, and he said that irrespective of what are the velocities of approach and velocities of separation, for a given pair, the coefficient of restitution is constant, right? So these are the two bodies, they are moving with a certain velocity. So here you have v2 minus v1 upon u1 minus u2, that is the velocity of separation, and this is the velocity of approach. This ratio is called as coefficient of restitution. Okay, it is applicable more or less in the inelastic collisions, right? For the elastic collision, the velocity of separation and velocity of approach is same, right? So A is equals to 1, the ratio is 1, right? In elastic collision, it is between 0 to 1, and perfectly inelastic, it is 0, right? So here it is. Now, if it is a perfectly plastic collision, perfectly inelastic collision is happening, yeah, then we can say that, irrespective of the type of collision which is happening, the momentum always stays conserved, which is the total momentum before collision stays same as total momentum after collision. I have explained that while explaining the law of conservation of momentum, right? I have explained that part while explaining the law of conservation of momentum, right? Okay. So you see that m1 u1 plus m2 u2 is m1 plus m2 into vf, because it is perfectly inelastic collision. Both the bodies combine and move ahead with one common velocity, which is vf, right? So this is how you will get vf, right? The total loss of kinetic energy, because the whole system is now moving with velocity vf. Before collision, individual bodies were moving with v1 and v2. So total system had kinetic energy half m1 v1 square plus half m2 v2 square. And now you have to subtract it minus half m1 plus m2 into vf square. That is the loss of kinetic energy that you're going to get. So this is for the perfectly inelastic collision. Now, if you have the elastic collision, then again conservation of momentum holds true again. So m1 u1 plus m2 u2 is equals to same as m1 v1 plus m2 v2. That is not going anywhere, and the kinetic energy of the system stays the same as well, because it is elastic collision. No part of the system's energy is wasted in deformation, right? Okay, this is how it is. E is equals to 1, right? Now in the inelastic collision, however, in the inelastic collision, however, what will happen? U1 and U2 will have different values like this. So generally they don't ask the questions in the NEET exam from the inelastic collision. However, if they do, the value of E will come into the picture. And however, even if the collision is inelastic, the conservation of momentum holds true in this one as well, right? So the summary of this whole thing is this: that collision is happening between two bodies. If we consider the whole system as one, so these bodies are going to apply force on each other and they will change their momentum for sure. But look at the system, then we will not be applying any force on the system. So the total momentum of the system stays same, right? Okay. Elastic collision is that where both the momentum and kinetic energy of the system maintains conserved. In the inelastic collision, kinetic energy is not conserved, only the momentum is conserved, right? Okay. So that's pretty much everything about the basics of Newton's laws of motion and power energy, right? These were the essential concepts. Yashwant, I don't know Telugu, right? I don't know Yashwant Telugu. Okay, by the way, these were the concepts that we had to discuss from the chapters of Newton's laws of motion and work, power, energy for the bridging purposes, right? We can discuss like around 5 to 10 hours on each chapter, right? Specifically when we are discussing those chapters. But our idea over here is to migrate you with the essential concepts into grade 12th, and that will give you essential confidence, right? Okay. Now, if you have any other questions regarding any of the discussions that we have done, you can ask it. Okay. If you have any other question regarding the discussions that we had, you can definitely ask it. All right. So I hope that's that, right? Let's keep the lecture till here only, right? I'll see you there in the next class with another bridge course class, right? Till then, take care, my dear kids, and bye-bye.